Inverse functions introduction. So let's move on to a new and very important topic, inverse functions. Now, as you recall from our previous discussions, we've spent some time understanding what functions are and how they behave. We looked at different types of functions, specifically focusing on whether they were injective, which we called one-to-one functions, meaning each input gives a unique output. We also explored surjective functions, also known as onto functions, where every element in the codomain is actually hit by some element from the domain. And finally, we combined those ideas to understand bijective functions, which are both injective and surjective. Building on that foundation, we're now going to explore what happens when we try to undo a function. That's essentially what an inverse function does. Think of it like this. If a function takes you from point A to point B, the inverse function takes you right back from point B to point A. It reverses the action of the original function. However, it's crucial to understand that not every function has an inverse. It turns out that only bijective functions, those that are both one-to-one and onto, actually possess inverses. We'll be focusing primarily on these bijective functions as we move forward, because that's where the concept of an inverse function truly makes sense and is well defined. We'll see why this is the case in more detail as we progress, but for now, just keep in mind that bijectivity is a key requirement. What is an inverse function? So let's move on to understanding what an inverse function actually is. As we discussed on the previous slide, an inverse function essentially reverses the action of the original function. Think of it like this. If you do something and then undo it, you're back where you started. That's what an inverse function does. We denote that is, we write an inverse function as f inverse. It's written as f with a superscript of -1. This f inverse is the function that undoes what the function f does. Now let's be a bit more precise. If a function f takes an element x from a set A and maps it or sends it to an element y in a set B, we write this as f of x equals y. Then the inverse function, f inverse, will take that y and map it back to x. We write this as f inverse of y equals x, so it perfectly reverses the process. Finally, and this is crucial, an inverse function doesn't always exist. It exists if and only if the original function f is a bijection. Remember from our earlier discussion that a bijection means the function is both injective, also known as one-to-one, and surjective, also known as onto. Formally, if we say that f maps from set A to set B, written as f, A to B, then its inverse, f inverse, will map from set B back to set A, written as f inverse, B to A. But again, this only happens if f is a bijection. We'll explore why bijectivity is so important on the next slide, and we'll also see how to actually find inverse functions with some examples. How to find an inverse function using sets. So now we're going to solidify our understanding of inverse functions with some examples, working directly with sets. Remember from the previous slides, an inverse function essentially undoes what the original function does. And crucially, this only works if the original function is bijective, both one-to-one and onto. Let's start with example 1. We have a function f that maps elements from set A to set B. Set A contains the numbers 1, 2, and 3. Set B contains the numbers 4, 5, and 6. The function f is defined by these ordered pairs. 1 maps to 4, 2 maps to 5, and 3 maps to 6. Now, to find the inverse function, denoted as f inverse, we simply reverse these ordered pairs. So, instead of 1 mapping to 4, 4 now maps to 1. Instead of 2 mapping to 5, 5 maps to 2. And instead of 3 mapping to 6, 6 maps to 3. Therefore, f inverse is the set containing the ordered pairs 4 mapping to 1, 5 mapping to 2, and 6 mapping to 3. Notice how the domain and codomain have switched. F inverse maps from set B to set A. We can write this as f inverse of 4 equals 1, f inverse of 5 equals 2, and f inverse of 6 equals 3. This confirms that f inverse truly reverses the action of f. Now, let's move on to example 2. This one is very similar, but uses letters instead of numbers to illustrate that the concept isn't limited to numerical sets. We have set A containing the letters B and C, and set B containing the letters X, Y, and Z. The function f is defined as follows: f of A equals X, f of B equals Y, and f of C equals Z. We can represent this function as the set of ordered pairs. A maps to X, B maps to Y, and C maps to Z. Just like before, to find the inverse function f inverse, we reverse these ordered pairs. So, X now maps to A, Y maps to B, and Z maps to C. Therefore, f inverse maps from set B to set A, and is defined as f inverse of X equals A, f inverse of Y equals B, and f inverse of Z equals C. These examples demonstrate the core idea: finding an inverse function by simply swapping the input and output values of the original function, as long as the original function is bijective. In the next slide, we'll explore why bijectivity is so important for the existence of an inverse. Why bijectivity is necessary. So let's move on to understanding why a function needs to be bijective, that is, both injective and surjective, in order to have an inverse. As we've seen in the previous examples, finding an inverse involves essentially swapping the inputs and outputs of the original function. But what happens if the function isn't well behaved? That's what we'll explore now. The core idea is this: a function must be bijective to have an inverse. Let's break down why, starting with injectivity, also known as being one-to-one. If a function is not injective, that means that multiple different elements in its domain, that's the set of all possible inputs, can map to the same single element in its codomain, which is the set of all possible outputs. Imagine several arrows all pointing to the same destination. Now, when you try to find the inverse, you're essentially trying to go backwards from that destination. But if multiple inputs led to that same destination, which input do you choose to map it back to? It becomes ambiguous, and you can't define a unique inverse. The inverse would not be a function, because a function requires a unique output for every input. Next, let's consider surjectivity, or being onto. If a function is not surjective, it means there are elements in the codomain, potential outputs, that are not actually reached by any element in the domain. Think of it as some destinations having no arrows pointing to them. If you try to create an inverse function, you'd need to map these unreached elements in the codomain back to something in the domain. But there is nothing in the domain that maps to them in the original function. So, the inverse would be stuck. It wouldn't be able to assign a valid input for those codomain elements. Therefore, to guarantee that an inverse function exists, we need both injectivity and surjectivity. Each element in the codomain must map to exactly one element in the domain. This is precisely what defines a bijective function. It ensures a clear, unambiguous mapping in both directions, from domain to codomain, and back again with the inverse. In the next slide, we'll see how this plays out with the composition of a function and its inverse, which will further solidify this concept. Composition of a function and its inverse. So let's move on to understanding what happens when we combine a function with its inverse. This slide explores the concept of composition. Now, remember from our previous discussions that composition means applying one function after another. We write this as f$ composed with f minus $1 of x$, and it's read as f of f inverse of x. The key idea here is that if a function f has an inverse, f minus $1, then when you compose them, either f$ after f minus $1 or f minus $1 after f$, you get what's called the identity function. The identity function, often denoted by I, is a very simple function. It just maps each input to itself. So, if you put in x, you get x back. It doesn't do anything to the input. Mathematically, this is expressed as f$ composed with f minus $1 of x$ equals x$ for all values of x that are in the codomain of f, and f minus $1 composed with f$ of x$ equals x$ for all values of x that are in the domain of f essentially. the function and its inverse cancel each other out, returning the original input. Let's look at an example to make this concrete. We'll use the function $f from example 1, which was defined as the set of ordered pairs 1, 4, 2, 5, and 3, 6, and we found its inverse $f-1 to be 4, 1, 5, 2, and 6, 3. Let's compose $f with $f-1. This means we first apply $f-1 to a value and then apply $f to the result. Let's take $x equals 4. So $f of $f-1 of 4. First, we look at $f-1 of 4, which from our inverse function is 1. Then, we apply $f to that result, so $f of 1, which according to our original function $f is 4. So $f of $f-1 of 4 equals 4. Let's do another one. $f of $f-1 of 5. $f-1 of 5 is 2, and $f of 2 is 5. So $f of $f-1 of 5 equals 5. Finally, $f of $f-1 of 6. $f-1 of 6 is 3, and $f of 3 is 6. So $f of $f-1 of 6 equals 6. Notice how in each case we end up back with the original input. Now, let's do the same thing but compose $f-1 with $f. Let's start with $f-1 of $f of 1. First, $f of 1 is 4, and then $f-1 of 4 is 1. So $f-1 of $f of 1 equals 1. Next, $f-1 of $f of 2. $f of 2 is 5, and $f-1 of 5 is 2. So $f-1 of $f of 2 equals 2. And finally, $f-1 of $f of 3. $f of 3 is 6, and $f-1 of 6 is 3. So $f-1 of $f of 3 equals 3. Again, we get back the original input. This demonstrates that the composition of a function and its inverse indeed results in the identity function, confirming that they undo each other. This is a crucial property of inverse functions, and it will be helpful as we move forward with more complex examples. Key takeaways. Let's recap what we've learned about inverse functions with these key takeaways. First, remember that an inverse function essentially undoes what the original function does. If a function takes an input and transforms it into an output, the inverse function takes that output and brings you back to the original input. Next, and this is crucial, only bijective functions actually have inverses. Now, recall from earlier that a bijective function is both injective, meaning one-to-one, and surjective, meaning onto. If a function isn't both of those things, it fails to have an inverse because either multiple inputs would map to the same output, or some outputs wouldn't have any input mapping to them. We need a perfect one-to-one correspondence for an inverse to exist. Now, how do we find an inverse? Well, when we're working with functions defined by sets of ordered pairs, the process is quite straightforward. To find the inverse, we simply swap the elements within each ordered pair. So, if the original function has an ordered pair of the form x, y, the inverse will have the ordered pair yx. We're essentially reversing the input and output. Finally, and this is a really nice confirmation that we found the correct inverse, is the concept of composition. If you take a function and compose it with its inverse, meaning you apply one function after the other, the result is the identity function. The identity function just returns whatever you put into it. So, if you input x, you get x back. Mathematically, we write this as f composed with f inverse of x equals x, and similarly, f inverse composed with f of x also equals x. This confirms that the inverse function truly reverses the effect of the original function. In the next slide, we'll look at some common mistakes students make when dealing with inverse functions, so make sure you've got these key takeaways solid before we move on. Common mistakes. The first mistake is trying to find the inverse of a non-bijective function. Now, remember from earlier, we established that an inverse function only exists if the original function is bijective. That means it has to be both injective, or one-to-one, and surjective, or onto. If a function isn't both of those things, it doesn't have a proper inverse. You'll end up with ambiguity or a relation that doesn't quite behave like a function. So, always check for bijectivity before attempting to find the inverse. Next, we have incorrectly swapping elements. When we find the inverse using ordered pairs, like we practiced with the set examples, it's easy to get mixed up. Remember, if the original function f maps x to y, written as f of x equals y, the inverse function, f inverse, maps y back to x. So f inverse of y equals x, you literally just switch the order of the elements in each ordered pair. A small error here can completely change the inverse function. Finally, and this is a subtle but important one, forgetting the domain and codomain. The domain of the original function f becomes the codomain of the inverse function, f inverse. And conversely, the codomain of f becomes the domain of f inverse. It's like the input and output have switched roles. Keeping track of these changes is crucial, especially when you start working with more complex functions and compositions. Let's move on to the final slide, which highlights some common mistakes students make when working with inverse functions. It's good to be aware of these before you get stuck, so we can avoid them. So, keep these 3 points in mind as you practice, and you'll be well on your way to mastering inverse functions. Are there any questions about these common pitfalls before we wrap up?